We're talking about root locus, but sometimes there's a little bit of upfront work you need to do before you just dig into root locus itself. So I'm going to talk about that in this video. It will deal with the parameter of interest. Sometimes you just skip over this. In fact, when I taught it, I kind of skipped over this just in the interest of time. But it's kind of interesting, and you should at least know about it, even if you don't have to do it very much. Remember, root locus is all based on this K times L of S. L of S must be monic in numerator and denominator, and the root locus is where are the roots of the closed loop system as this K goes from 0 to infinity. The upfront work is coming up with this L. There were kind of three possibilities. If you had this basic group and G and H or its product already had monic numerator and denominator, and this K was what you were interested in, then everything's easy. L for root locus is just the loop transfer function, which is G times H. Well, actually with the K taken out. But the L is just the product of G and H, and the root locus K will be this K. Slightly harder is if G and H don't have monic, the product doesn't have monic numerator and denominator. You just need to multiply by some constant to make the GH, to make the whole thing monic and numerator and denominator. That's the L. In that case, the root locus K will absorb this little K. We did those examples before. The third bullet is what I'm going to talk about. It's this parameter of interest analysis. Let me get to an example. Here's an example. This, for example, could be a controller that's proportional plus integral control. We'll get into that a little bit later. And here's our plant, let's say. It's in a unity feedback configuration. Look at the forward path. Its transfer function is this. Unity feedback, so you could do a little bit of steady state error analysis. You can look at it, know it's a type 1 system, and then you take that out of it, evaluate it at S equals 0, you get 6 over 6, which is 1, or it's just K sub I. That's your error constant for that type 1 system. So this K sub I is your error constant. So let's say you chose that K sub I to meet some steady state spec. And now you want to know, where do the poles of the closed loop system go in the complex plane as Kp goes from 0 to infinity? K sub P is now my parameter of interest. And if you do the analysis, here's the characteristic equation in this form as a single polynomial. Kp is our parameter of interest. We only have one parameter of interest at a time. Here's the basic method for parameter of interest analysis. You isolate it in the characteristic equation and divide through by all the other terms. Here was our characteristic equation. First, let's isolate the K sub P. Here it is, isolated. All these terms don't have K sub P in it, and this is all one term with K sub P. Now divide everything by all this stuff, everything but the K sub P term. That upfront part will just cancel. This is all one, and you're left with this thing. Now this is in the form, in fact, see this part? Monic numerator, monic denominator. This is in the form we wanted. So this is our L of S. And our root locus K is going to be 6 times K sub P. This is the L of S we use for root locus analysis. It's not just simply P times H. If conversely K sub I was the parameter of interest and K sub P was some constant we determined some other way. Let's see, this would be the characteristic. K sub I is already isolated, divide everything by this. So now this is our L of S. And our root locus K is this 6 times K sub I. I'll do one more example. Let's say this is our forward path, but oh look, one of the poles in the forward path is our parameter of interest. We want to know how the poles of the whole closed loop system vary as we vary this closed loop pole, is A. Actually, pole would be a minus A. As we vary this A from 0 to infinity. So here's the characteristic equation, the denominator plus the numerator. Multiply everything out and isolate A. Divide by this upfront part, I get a 1 plus A times this stuff. And that part is monic numerator, monic denominator. That's our L of S. Our root locus K is exactly that A. Here's our L of S. Again, it's not simply G times H. You have to do a little bit of upfront work. So while that L of S in general depends on what your parameter of interest is, in most or all of our subsequent problems, our parameter of interest is just going to be some gain in the forward path. Gain meaning some multiplier of everything in the forward path. Like this example. And here, these two parameters were not simple gains that multiplied everything in the forward path. So we had to do a little bit extra work. Now, if you're finally, we've got what we need to start really doing root locus. We're going to learn how to do root locus by hand. That will come in later videos. And root locus always starts with that L of S. And this K is our root locus K. So we'll do this starting next video. Now we're ready to start real root locus by hand.